In this video, this is the third part of our lesson on zeros of polynomials. And I promise this one's going to be a lot shorter. I know that the first two got kind of long. And so the last part of this is just understanding how many zeros a polynomial will have and the behavior of imaginary zeros. So this is exactly where we dropped off or left off from our part two, was looking at the properties of zeros. And I want to say that I've mentioned this in the previous parts, but now I want to make it a little bit more explicit. It's written down, it's in the notes. A polynomial of degree n has exactly n zeros, possibly counted multiple times. So, like, if you have a degree 3 polynomial, it must have 3 zeros. Now, that might include something with a different multiplicity. So it might have 2 unique zeros and 1 zero that's counted twice because it has a multiplicity of 2. That is definitely possible. It could have 1 real zero or 1 rational zero and 2 imaginary zeros. So there's different options. There's different things that are possible for your zeros. If I have a degree 5 polynomial, I would have 5 zeros. Okay. So, and that could be a mix of rational, irrational, and imaginary. So just keep that in mind. The second part of this is if a plus bi is a zero, then so is its conjugate, a minus bi. So when you're asked to find a polynomial f of x of degree 3 with real coefficients in the following zeros, and they give you the zeros -3, 1, and 2, it has 3 zeros, so that matches our degree. We've met the property, the first property. To write the actual polynomial, we would say f of x equals, and then we would take each of these and write them as their factors. Now remember, when you write a zero as the actual factor from the polynomial, these are our C values. So when I have x minus -3, that would actually be written as x plus 3. Some people notice that pattern where the factor, if the factor is adding, the zero is negative. If the factor is subtracted, then the zero is positive. So we would just write out these factors. So I'd have x plus 3, x minus 1, and x minus 2. Now you could multiply that out, but oftentimes in ALEKS they'll just tell you to write the polynomial. If they don't say fully expand, then you could leave it just like that. So if you're asked to find a specific polynomial where, let's say they say f of 1 equals 120, because what's assumed here is that if they don't tell you a value, then you just write it like this, like I wrote before. But if they give you a specific value, then you have to find what your leading coefficients should be. So what you would do is you would then replace all the x's with 1. So I'd have, if f of 1 equals 120, I would have 120 equals a sub n, my leading coefficient, times 1 plus 3 times 1 minus 1. Well, this isn't a good example. That wouldn't be possible. Let's say if it's an f of 2. No, that wouldn't be possible either because I keep getting zeros, which is not going to be good. Let's say they said f of 3. So then it would be 3 plus 3, 3 minus 1, and 3 minus 2. So I would end up having a sub n equals 6 times 2 times 1. So a sub n times 12, because 6 times 2 times 1 equals 12. I picked a good one now, because this is going to be evenly. I would then divide both sides by 12 to find out what my leading coefficient would be, and in this case, my a sub n would have been 10. So if they ask for a specific polynomial, they'll give you an evaluated result, and you work backwards to find that leading coefficient. If they just say find a polynomial, you don't need to find that leading coefficient. Okay, so just keep that in mind. All right, now is where things get a little bit tricky. If they give you the zeros as terms that are imaginary, as imaginary values, you have to see what happens when you multiply out each of these expressions. So when I have x minus 3i times x plus 3i, this is going to equal x squared plus 3ix minus 3ix minus 9i squared. Well, minus 3ix plus 3ix is 0. So I'm left with x squared. And then I squared is equal to negative 1. Because if I have I is equal to the square root of negative 1. And if I square that, that's equal to just negative 1. So negative 9 times negative 1 is equal to plus 9. So if you multiply a imaginary number times its conjugate, the middle terms cancel out. And if you use the quadratic, or if you solve this, like x squared plus 9 equals 0, you subtract 9 from both sides, you get x squared equals negative 9. And when you took the square root, you'd be taking the square root plus or minus the square root of negative 9, which is going to be plus or minus 3i. So your factors would be x plus 3i and x minus 3i. So that should hopefully make sense. But that's what happens when you multiply conjugates times each other. When you multiply b out, you have to distribute twice. This gets a little bit more complicated. So I'm going to do the algebra and then show and talk through the answer. Okay, so what I did here is I distributed the x. So x times x is x squared, x times negative 2 is negative 2x, and x times negative 4i is negative 4ix. And then I did the middle term in purple. Negative 2 times x is negative 2x. Negative 2 times negative 2 is plus 4, and negative 2 times negative 4i is plus 8i. And then I did the last term, the plus 4i times x times negative 2 and times negative 4, and I did that in blue. And I lined them up this way so that you could see what happens. What I'm doing is kind of adding these columns together. So x squared stands alone as it is. Then I would have minus 4x. Minus 4ix plus 4ix is 0, so those would cancel. So then I have a plus 4. Then I would have plus 8i minus 8i, those cancel. And then I would have minus 16i squared. So again, an I squared is the same thing as negative 1. So negative 16 times negative 1 is plus 16. I don't know why I wrote 12, plus 16. So then I can combine my like terms right here. So I would have x squared minus 4x plus 20. So notice I get a regular quadratic, a regular looking quadratic. But then if you work backwards and use the quadratic formula on that, you would get a imaginary result, imaginary 0. So knowing that, now we're asked to find a polynomial f of x with degree 3 with the real coefficients and the following zeros. They give us negative 2 and 5i. Now remember, a degree 3 polynomial must have 3 zeros. And so right now, I know I have x minus c for the negative 2, which is going to be x plus 2. Okay, but then that 5i, remember, we're told that if a plus bi is a 0, then a minus bi is also a 0. So here I would have x minus 5i as a 0 and x plus 5i as a 0. Or as a factor, sorry. Let's say it as a factor, which gives us our 3 factors, which would give us 3 zeros. And then again, we know what happens when we multiply out x minus 5i, x plus 5i. That's going to give us x squared plus 25 based on what we just saw. So I could write this as, because it says with real coefficients, this one would want to be written all the way out and expanded all the way out. Now I can multiply these two binomials. X times x squared is x to the third. X times 25 is plus 25x. 2 times x squared is 2x squared. 2 times 25 is 50. I could rewrite this so that it's in the correct descending order. X to the third plus 2x squared plus 25x plus 50. Now remember, this one didn't tell us like an f of like 3 equals something, so I can't solve to find the leading coefficient that would be assumed to be out here. So this one would stand because it just said to find a polynomial with these zeros. We could assume that we found the polynomial that has the leading coefficient of 1. With the only time we would not assume that is if they told us to evaluate it at a certain number. Now we have find a polynomial f of x of degree 4, which means we need 4 zeros, with real coefficients in the following zeros. So I have 1 that has a multiplicity of 2, so that's going to be x minus 1 squared is one of the factors. Then I have 3 minus I as a 0, so that's going to be x minus 3 minus I, and it's going to be x plus 3 minus I. And that's real pretty. Then you can multiply all of this out. Unless it just tells you to write the polynomial, you might be able to get away with just writing it out like that. If not, you'd have to multiply out these things. Now, this is a binomial squared, which you know how to do, and based on our previous example, you should be able to multiply that out as well. Anyway, you could distribute these negatives into these polynomials. So I would have x minus 3 plus I, and for this one I would have x plus 3 minus I, because that wouldn't change their signs for that last one. So I could write it like this, and then you can multiply it out. And so that is finding polynomials based on their zeros and the zeros multiplicities, and the fact that if you have an imaginary 0, you also have its conjugate as a 0 as well. So hopefully this helps you get through your topics this week. If you have any questions, just let me know. Thank you.